intertwined patterns of integers and patterns of thought processes. So without any further ado, please.
It's a pleasure to be here and an honor and a little intimidating to be among so many highly accomplished mathematicians, because I dropped out of math graduate school I had been deeply fascinated by mathematics ever since I was a kid, but I found the challenges of math graduate school a little bit too difficult. So it's an honor and almost a bafflement to me as to why I would be the keynote speaker, except I will say that sequences of whole numbers have been an incredibly central part of my life in different phases of my life and in different fashions. So I will just explain that. It's sort of an autobiographical talk, which is a little random walk among certain types of sequences. I must say, I'm a little too old to have been formed by the handbook or encyclopedia or online encyclopedia of integer sequences, because I did most of my explorations of sequences before the book appeared. But nonetheless, I am an occasional minor contributor to the book through some of the sequences that I've explored. And there have been so many. I mean, in preparing this talk, I went through large files of things that I'd explored and saw that there were just gobs of them. Many of them I couldn't figure out from my scribblings what on earth I was doing, but that's the way it was. I didn't document them as well as I would have liked, but I certainly know some of them extremely intimately. So what I will say is that as one of the things I will conclude with is talking about how my passion for sequences, which started when I was around 15 or 16, that number seems to appear in the life stories of many people. When I was a 15-year-old, when I was a 16-year-old, same for me. So the passion lasted for quite a number of years, and then it sort of went dormant, but it came back when I was a graduate student in physics, and it was that passion that gave me that made me be the right person at the right place at the right time, and I made a lovely discovery, which I will show you here. I can figure out how to make this thing work. I think I can. Yes. Okay. This was something that I'll talk about just very, very briefly when I come to it again later on, because it's out of chronological order. But it's a rather spectacular looking graph, sort of a multifractal as it is called, and I called it G-plot when I found it, and that's what I always still call it. But many people call it the Hofstadter butterfly, so that's nice. And it's closely related to things that I did when I was exploring integer sequences. So now I'm going to begin that story. So we begin with something that everyone knows, the triangular numbers, which of course are in the handbook. I had a friend, actually John Mather of the Princeton math department at the time. He was just a couple of years older than me, and he was starting Harvard. He and I exchanged some letters, and we were talking about triangular numbers, and I got very interested in them. And for some reason that I don't remember, I decided to interleave them with the squares. And so there they are on the lower level. The red ones and the squares are the blue ones above. Actually, I wonder if the sequence of interleaved triangles and squares is a sequence I doubt that it would be, but it's a possibility. To me, it's something very familiar, although it is a two-level sequence, so in a sense it's really not one sequence. In any case, I was counting the number of reds between blues and allowing, when they coincided, I would draw a line on this side. I guess I could lose this thing. So anyway, it doesn't matter.
Just to tell
yes.
you, is using the OIS
It is.
with a reference to Analogies.
Oh, okay. I'm curious. All right. So there you see what happens when there are, when you count triangular numbers between squares, you get the sequence at the bottom, 2, 1, 2, 1, 1, 2. And you should memorize that because it will come back later. So I'll show you, if I recall correctly. There it is again. And I've just highlighted the 2 1s that are there. And, you know, as a kid, I explored this just empirically. I did it by hand at first. I got about, I don't know how many terms, probably 100 terms by hand. And then I used a mechanical calculator, and then I used a computer later. But I didn't really need to use the computer. I mean, by the time I had done it even by hand, I could see what was going on. It took me a couple of days. And I was extremely excited when I realized that if you counted the number of 21s between the two 11s, you got back the same sequence. In other words, I guess I can try this thing out now if I understand it. There's one. There are 2 of them there, 1 of them there, 2 of them there, 1 of them there, 1 of them there, and 2 of them there. You see what I'm pointing? Does that work for you? Okay, so 2, 1, 2, 1, 1, 2, and there, that is the sequence itself. And that was a fabulously exciting discovery for me as a 15, 16-year-old. And of course, I wanted to experience it again. So I did, you know, I'm talking about analogies, so many of my analogies were a kind of a natural thing to do, which is to spot a knob and then twist the knob to other settings. And so triangle is a knob which says 3, and square is a knob that says 4. And so I just thought, well, let's set the knob at 5 and see what happens. Either count triangles between pentagonal numbers or count squares between pentagonal numbers, and so forth and so on, with higher level polygonal numbers. And you can generalize this algebraically also, and I did it both ways. I mean, I saw that they were equivalent. And I found sequences that had some similar properties, but they didn't give themselves back as this one had done by counting something between something. And so I was a little disappointed. So, I was doing many things in parallel. More or less in parallel. One of them that I next tried was found another knob on the original problem. That is, the triangular numbers were the sums of numbers up to n. Well, I just said, well, let's look at product instead. And Michael Somos already talked about the double factorials. I wasn't aware that that was the name of them, but you know, the products of odd numbers, and that's what you do if you replace the plus signs with times in the squares. Instead of 1 plus 3 plus 5, it's 1 times 3 times 5. So that was the analog of the squares, and then I counted factorials in between odd number products, and here you see something. No, it's not working. Is it? It likes my right hand. It doesn't like my left hand. Okay, 2, 1, 1, 2, and so forth. I'm not going to go into this one because, again, although it had some curious properties, I didn't find anything fascinating about it. I'm just sort of showing you, carrying you along with me as I make a sort of a meandering walk and trying to find interesting things. So the next thing I thought of was going sort of one level of generality above polygonal numbers. I just thought, well, why not just polynomials? Just count one polynomial in one variable between another polynomial in one variable. And I thought about that, didn't explore it too much, but it led me to the next level up in abstraction, which would be count values of one function of one variable between values of another function. And so I thought, well, what's some simple functions? And powers of 2 and powers of 3. And so that was my next exploration. Then we had the same kind of thing, and then we see a sequence 2, 2, 1, 2, 1, 2, 2, and it looked kind of interesting. And I just go through a little bit of calculation here to say that the kth term, and it really does not like my, oh, there it is. Okay. I've trained it. Okay, so if alpha is log to the base 2 of 3, this is the formula for the kth term of this sequence, where the brackets indicate the floor. So I'm not going to show this sequence. Because it has some. It's confusing if you look at. I'm going to take a similar sequence of counting powers of 4 between powers of 5, and you may not be able to tell, but these are 1s and 2s, and I made the 2s a little bit bigger. So now if you count them, you get there are 5 of them here, 5 of them, 5 of them, and 6 of them, and 5, 5, 5, 5, and so forth. So you get another sequence that looks kind of similar, except that it's made of 5s and 6s. And now if you count the 5s between 6s, you get 4, 4, 3, 4, 4, 3, and so forth. And in that sequence, if you count 4s between 3s, you get 2 and something else. So it seems as if what you get each time by counting the thing whose density changes between the... well, let me just give you some terminology. The thing that occurs individually I call a sep. The 6 here is a sep, and the 5s are counds, because I'm counting them. So you count counds between seps, or separators. If you count the counds between seps, you get these things I call eta sequences. So you get another eta sequence, and it keeps on going. Now, before I explain any more about eta sequences, I wanted to just again talk about analogy making a little bit. If I go back to this formula here, I've actually written it in a way that maybe I wrote it this way, but maybe not. I think I didn't have the alpha there. I think I put log 2 right there and right there. So to me, there was no alpha there. There was just log to the base 2 of 3. And I remember I was in the office of my friend and mentor, Gordon Latta, who was on the faculty at Stanford. And I was showing him these things, and I was saying I was generalizing, making a generalization of this kind of thing by, varying the 2 and the 3. Those are the knobs I saw. I saw 2 integer knobs. And Gordon Latta said, "What are you talking about? Your variable here is alpha. It's a real number. That's what you should be." Of course, log to the base n of m is a dense subset of the real line in any case, and I would have realized that perhaps sooner or later that I can get as close as I want to any number, so I might as well just let alpha run over the real numbers, and so I did, and that was the beginning of a lot of exploration, a great deal of which I can only touch the surface. But that was my definition. The kth term of the eta sequence of alpha is k plus 1 alpha minus k alpha with the greatest integer function attached to both of those. And as I said, it's composed always of 2 integers, the count, which is, by coincidence, has the letter C for closest, and the sep, which by coincidence has the letter S for second closest, so we have count and sep. You can think of C as standing for closest, and S as second closest, or C as count, and S as sep. In any case, so if you take the eta sequence of the square root of 2, it consists of 1s and 2s, 1 being more frequent because it's the closer integer. For the golden ratio, it's the other way around. For pi, it's composed of 3s and 4s, with 3 being more frequent. For e, it's composed of 3s and 2s, with also 3 being more frequent. And so the fundamental theorem was, well, first of all, I guess I'm showing the derivative process, which is you count the number of counts between successive seps, and yes, it's a different eta sequence, and this is the fundamental theorem that if you take that derivative, as I called it, the derivative sequence is also an eta sequence with a different alpha, which is sep minus alpha over alpha minus count. And that is the rate, the distance to the second closest integer divided by the distance to the first closest integer, and that's always greater than or equal to 1. And I'm always thinking about alpha as being an irrational number, so that you could take the derivative an infinite number of times. If it was rational, the process would terminate at some point in an integer. But those integers interested me less, so I'm just going to concentrate on the case of irrationals. So this was a sort of a vertical structure that you got that was associated with any alpha that you began with, the count and the sep, and then you would take its derivative, alpha prime, and then take its count and sep, and then take that number's derivative, and take its count and sep, and so forth. Now, of course, I was very curious to explore this. Here's an example, just the square root of 2, since it turns out that the sequence is its own derivative instantly. And so, since it is, the counts are always 1, and the seps are always 2, on all levels. And incidentally, this you can make a sequence of counts and seps, any arbitrary vertical sequence of counts and seps that you want, as long as they differ by 1. They always have to differ by 1, and they always have to, the lower of the two has to be at least 1. And so this was a nice fact. I could write down any sequence of counts and seps I wanted, as long as they obeyed those little constraints, and they would determine a real number for me. This second example is for the golden ratio, and it is the reverse. The two numbers, the square root of 2 and phi, are in some sense complementary to each other. Needless to say, I wanted to explore other numbers. I immediately tried E, and I was working at this time, it was about 1961, with a Burroughs computer at Stanford. It was the only computer that Stanford had, and it had about 10 or 12 decimal digits of precision, and I was able to calculate the count in the sep sequence as far as it shows here. And on the left side, I wasn't, I could see some kind of pattern where the ones seemed to be sort of starting to go every other term, and on the right side where the 2s seemed to be going every other term. But I was particularly struck by the right side, because I saw that if you eliminated the every other term 2s, you had 2, 3, 5, 7. And that was a sequence that maybe some of you have heard of before. 2, 3, 5, 7, and I was thinking, oh my God, E contains the prime numbers. And so here was this cartoon I found some years later, but from the New Yorker, and this really was the feeling that I had, depending, of course, on how far down it goes. And so, in order to find it, empirically, I had to do higher precision, but at that time, it was very difficult. I finally found a triple precision arithmetic routine, which consisted of about 400 cards. I was programming on cards, of course, that I had to put at the back of my program. My program was probably 20 cards long, but I had to append 400 more cards, and it would read it in and then do it. And so, thanks to that triple precision routine, I could extend it, and here's how it came out. 2, 3, 5, 7, 9, 11, 13, 15. And so it was still pretty, but not quite as exciting as it had been the prime numbers. I've often wondered, by the way, and I'm sure many of you have often wondered, whether in some sense the exact way that the prime numbers begin matters. That is, it seems it seems as if nature doesn't really care about how the prime numbers really start. What nature cares about is how they're distributed after, sort of asymptotically. It doesn't care that the first one is 2 or something like that. So that 2, 3, 5, 7 was that was sort of my reading too much into that thing. But anyway, it was exciting, and it gave me the impetus to continue exploring. As I told you earlier, the square root of 2 and phi were each other's complements. That is, the count of 1, the vertical sequence of counts of 1 was equal to the vertical sequence of seps of the other. And so I thought this would be an interesting thing to try to explore. What in general, since if I knew I could exchange count and sep sequences, and there would be a number that would have the exchanged columns, so why not see what happens? And we didn't have plotters in those days. Everything had to be done by hand. So I got out numbers and I plotted them, and I'm not going to show you my hand plots, but years later I reconstructed sort of the kind of thing I saw when I first did this. and it looked about like this. And I didn't really know how to interpret it, and I wasn't thinking terribly hard. I was more just calculating and drawing the points. I didn't have this many points. I didn't see this much accuracy. But I did see that it sort of consisted of little streaks, you might call them ribs or something like that, and they got smaller and smaller as you went toward the corners of this square between 0 and 1. And so I wanted to know what the little streak like that looked like in greater detail, so I had the computer calculate it for me, and it got something like that. And then all of a sudden I saw basically that this was going to go down and down and down and continue. And so eventually, some years later, when we had nice plotting equipment, I was able to make nice plots of it, and this is how it looked. And I was able to prove how this thing was nested inside itself infinitely many times, and what the exact nature was of the curve, that because it's curved, it's sort of distorted. But despite the distortion, it still, in some sense, is the same object, just distorted a little bit. And so that was a very exciting discovery for me. This shows you where the copies are located, which, in case it wasn't self-evident, but it shows it on more than one level. You can see it down there too. You can see the squares encasing the other copies, and it keeps on going down, down, down. And when you get closer and closer to the corners, this thing gets less and less distorted, and so it's more straight. I generalized data sequences to two-dimensional structures, made Ada lattices, proved a theorem that in some sense there was a kind of a derivative of Ada lattice, which was another Ada lattice with these had two real parameters now, and I was able to show that the derivative, in a certain sense, of the term was another Ada lattice, and so that was interesting to me too. But on I went. Shifted data sequences, just cut off the first few terms. Like if you cut off the first 6 terms of the data sequence of the square root of 2, you basically are just shifting it by 6. So you can move 6 times the square root of 2 over to the right side. And it's sort of a shift by a delta. So I generalized the idea of an data sequence to have a shift of delta, where delta was any real number, and it didn't matter. Its integer part didn't matter, since that was ignored by the floor thing, but its fractional part was what counted. And I was able to show that, again, if you create an Ada sequence of this form and took its derivative, it would again be another Ada sequence with an alpha prime and a delta prime. So you had the fundamental theorem still held. Coming full circle, it was exciting to me that finally, when I had defined this thing, I found that the Ada sequence of the square root of 2 with a shift of a half was my original triangles between squares sequence. This was shifting it out, but shifting it out infinitely far, because no finite shift will give you a half, since all integer multiples of the square root of 2 are irrational, so you'll never get a half as your delta. But if you put in a half, you get back triangles between squares, and I was able to prove that, and I was very happy. Now, among the other, I was doing many things, exploring all sorts of sequences, which I don't have the time to go into, but one of the things that I got into was playing a game with some of my friends who were interested in mathematics, which was basically, we called it the function game, and the idea was that you would invent a formula using a certain vocabulary of symbols, and then your opponent would have to try to figure out what your formula was, or at least an equivalent formula, by probing the function at certain values, or by asking certain kinds of questions that were allowed. There were certain kinds of questions that allowed, and the more questions they took, the lower their score, and the lower, the simpler that the function looked in terms of the symbols that you used, the better it was for you as the function creator. I mean, obviously you can create a very complicated function with a lot of symbols, but if you use very few symbols to create a very, very mysterious function, that was good. And we played the game many times, explored it. One of the things we allowed was recursion in our definitions. And so I invented this on a lark one day. I had no idea what it would give, but this cost. It was fairly cheap because it didn't use many symbols, but it had a very peculiar behavior, and it started me out on another set of explorations. So here's sort of a value. This is a tree which shows sort of how the function, the values of the function are oriented. Where, for example, again, the f of 14 is 9, f of 9 is 6, f of 6 is 4, and so forth. I don't know if you can read these numbers. If you can't, I'm sorry. But if I wanted to calculate, for example, there's 21, if I can read it myself. I'm in a very strange angle, but that's 21, isn't it?
Yeah.
So if I wanted to calculate f of 22, I need to take f of, or I should say g of 21. So I have to start here. I'm sorry, I've said this wrong. If I want to calculate g of 22, I have to take g of 21. So I go down one and go down another, and that gets me to 8. And of course, you can see the Fibonacci numbers along here. So I get to 8, and I subtract it from 22. And that gives me the value, and that's 14. And so I put it above here. Now, if I want to do it for 23, I do the same thing. I go down from 22, 2 steps, and then subtract it from 23. And that's 14 again, and so 23 goes here. So I get a fork above the 14. For 24, I would go down twice, get to 9, and subtract it from 24, and I get 15. So 24 goes above here, and so forth. I mean, so I originally made the tree just as a convenience for calculation. In other words, if I want to know g of n, I just look two levels down. Instead of looking in a table, I have a display which makes it easier. But it turned out, of course, that the shape was of interest. And so if I replace, well, let's see. Basically, it's a recursively structured shape, which is, you can define it by saying that you see there are trunks and there are bifurcations. On the left side of every bifurcation is another bifurcation, and on the right side of every bifurcation there's a trunk. So this sort of shows it here, although it does it with one level, extra level of recursion indicated to make it a little simpler to understand. Here's the simplest version of all. It just says here's a bifurcation. On the left you put the tree itself, and on the right you put the tree itself, but after one vertical step. So that's the full definition of the structure. Now, I asked myself questions like, what would be the recursive function if I flipped this and I made the mirror image of this tree? What recursive function would give that? And I was able to find an answer to that. And so the flip tree question was one in general that I was interested in, but in general I was unable to answer that question. It was very difficult. The fork function is you just put the multiplicity of the node. You write 2 whenever it's a branch, and you write 1 whenever it isn't. And so it turns out that the sequence here, 1, 2, 2, 1, 2, is, there it is. If you read it, go up each level, go left to right, go left to right, each time going like that. That's the Eta sequence of the golden ratio, with one term missing. There's a 2 there at the very beginning that's missing. And here's another way of seeing that fork, the pattern of forking. So these were nice discoveries. I wanted again to experience it, so I saw a knob in the function definition that I had created, which was, of course, that there was 2, and so I made it 3. And that gave me this tree, which was very similar. It was, in fact, almost identical, except that now the trunks were of height 2, where previously they had, or it depends on how you count it, height 3, you could say height 3. In any case, this is I call this the H function, and so this is the recursive structure of the tree for the H graph. And again, you can ask all sorts of questions about what is the forked function for this tree, what is the recursive definition of the flip of this tree, and so forth. And I got very involved in exploring, in general, these kinds of trees. I mean, since I'd already seen one whose fork function was an Eta sequence of the golden ratio, I tried sticking in other numbers as and making their eta sequences be the forward function for trees, and then seeing what kind of function I got out. Sometimes it was very interesting, but it was a little too complicated. Actually, I found that it was already hard enough if you simply used